Chemical nomenclature. Let's just jump right in here. I'm going to give you a little bit of a warning now. Chemical nomenclature is not the most exciting topic. It's not going to have any groundbreaking, earth-shattering revelations of the chemistry of things around you or anything like that. It really is bookkeeping. But everything has to have bookkeeping. Everything has to have some nomenclature, some way where you can tell the difference between one thing you're studying and another thing you're studying. As we'll see a little bit later in nomenclature, it's not good enough to say we have a molecule of nitrogen and oxygen. It's like, well, what molecule of nitrogen and oxygen? There are literally dozens of molecules that are made of nitrogen and oxygen. We have to have some way, some very well-designed, systematic way of naming molecules so that everybody knows what everyone else is talking about. And so even though it isn't terribly exciting, we still need to know how to name stuff. So we're going to start here by talking about how to name the simplest kind of ionic compounds. These are what we call binary ionic compounds. The way that you name these, thankfully, is pretty straightforward. You just take the name of the metal, and then you take the name of the nonmetal. You take the ending of the nonmetal, chop off the end of the name, and replace it with "ide." By the way, real quick, when I say binary, binary refers to just having two things. So you have just a single nonmetal and a single metal. Now, when I say a single metal and a single nonmetal, I don't mean a single atom. I mean a single kind of atom. So we can have more than one, like the example we had in the last video, which is MgCl2. We have more than just two atoms here. We have one magnesium, but then we have two chlorines. This is still considered binary. It's still considered to just have two things because we just have magnesium and chlorine. We don't care that there's more than one chlorine as long as it's not, magnesium, chlorine, and fluorine. That would not be a binary ionic compound. That does exist, by the way, but we are not going to worry about naming those kinds of molecules. So, excuse me. Sodium and chlorine is what we're looking at here as an example. So the sodium is the metal. The metal's name does not get altered at all. We don't mess with that one. We just take the name of the nonmetal, which is chlorine, take the "ene," the ending here, and we replace it with "ide." And so sodium and chlorine becomes sodium chloride, which I am sure you have heard of at some point at least. You might not hear about it all the time. The scientific name anyway, but that is table salt. That is sodium chloride. So we have a few other examples here. I think I'll do one of these other ones and I'll let you practice on the next three here. So the first example is sodium and fluorine. And by the way, notice these are the same examples that we worked out the structures for in the last video. So we have sodium and fluorine. That is sodium fluoride. So sodium fluoride. Calcium and bromine is the next one. Remember, we don't change the name of the metal. So this would be calcium bromide. And by the way, I don't think you're actually supposed to capitalize the beginning of bromide there. That just kind of did that instinctively. I'm not sure why. I don't think it's necessarily wrong, but you're not supposed to. Alright, so with that in mind, why don't you give these next three a try. Go ahead and pause the video and see if you can work out the names. Alright. Well, it'd be helpful if I spelled it right. Strontium and magnesium. So notice I'm writing the names of the metals first. It's just to point out we don't do anything to the names of the metals. The metal names stay exactly the same. It's the nonmetal that gets changed. So this is calcium sulfide. So sulfur becomes sulfide. This was phosphorus. And actually there's a typo there. Sorry about that. That should be P2. So strontium phos. And I'm really misspelling things for some reason. Phosphide. Sorry, that's kind of messy. So phosphorus becomes phosphide. Now, if you wrote down phosphoride instead of phosphide, I would still count that as being correct. As far as I am aware, the only reason we do phosphide instead of phosphoride is just people preferred it. I don't think that there's an actual legitimate scientific reason why they use phosphide instead of phosphoride. And you are following the rules if you just do phosphoride, because you chopped off the end and replaced it with ide. With phosphide, you're chopping off not just the end, you're chopping off like half of the word. So I would not count it as incorrect if you did phosphoride, but technically it is phosphide. And then the last one here, magnesium nitride. So nitrogen becomes nitride. So notice here that these subscripts have no effect on the naming. Because there is only one way that these molecules can come together to, or there's only one way that these ions can come together to make a molecule, we don't need to specify how many of the ions we have. Magnesium and nitrogen can only come together like this. There's no other way. Because if you try to do it any other way, then you're not going to end up with a net neutral molecule. This is the only possible way that magnesium and nitrogen alone, just the two of them, can come together to make a molecule, and so there's no reason to specify how many you have, because that's the only possibility. So there's no reason to say magnesium 2, nitrogen, or magnesium 3, nitrogen 2, nothing like that. Just magnesium nitride is fine. That's not the true for all metals, though. There are some metals that actually do have the possibility of having different charges. And this is mainly in the transition metals, although it's also true for a few of the metals that are down beneath the nonmetals, which we'll talk about in just a second. But mainly in the transition metals, you have metals that can have more than one charge. So iron, for example, iron can be +2, or iron can be +3. And it is perfectly happy to be one or the other. It's not like, 99% of the iron is +3 and only 1% is +2. No, it's perfectly fine to be either way. Doesn't really care. And so iron +2 and iron +3 can both react with chlorine. If we have iron +2 react with chlorine to form an ionic compound, we get this. If we have iron +3 react with chlorine, we get this. And those are not the same molecule. They will have fairly similar chemistries, but not identical by any means. They are most definitely completely separate molecules that just look very similar. So we can't both, they can't both be named iron chloride, because we need to be able to specify which one we have. So anytime we have an ionic compound, and again, ionic compounds are when we have a metal and a nonmetal. So in this case, our metal is from the transition metals, where it's possible for them to have more than one charge. Anytime we have an ionic compound with a metal that could have multiple charges, we are going to have to specify the charge on that metal. And we do that by using Roman numerals in parentheses after the name of the metal. So in this particular molecule here, we have iron with a +2 charge, and so this molecule is called iron 2 chloride. Now, it is just coincidence that the name is iron 2 chloride and we have 2 chlorides. The 2, again, is telling you the charge on the metal. It is not telling you how many of the nonmetals you have. Because something like this, for example, that is a molecule that exists. This would be iron 2 oxide. And obviously we don't have 2 oxides there. The oxygen would have a charge of -2 because this is iron 2. The charges balance out. You just need one of each. The number in the parentheses is the charge on the metal, not how many metals you have or how many nonmetals you have. It is the charge on the metal. So iron 3 chloride is this molecule, because we have a charge of +3, and so it takes 3 of the Cl minuses to balance out that charge and give us a net neutral molecule. All right, so let's do a couple examples here, and then I'll let you do the rest on your own. So the first one here, we have CuO. Cu is copper. O is oxygen, which is going to turn into oxide. So then the question becomes, how do I know what the charge on the copper is? Well, we know what the charge on the copper is because of the nonmetal. We can use the nonmetal to determine the charge on the copper. So in this molecule, for example, we know we have oxygen, and we know that oxygen wants to be -2. It's in column 16. Everything in that column wants to gain 2 electrons to be like a noble gas. So we know that the oxygen wants to be -2. Not only that, we know that this whole molecule must be net 0. The charge on this must be 0. So if the whole molecule has to be 0, and we know the oxygen is -2, that means that the copper must be +2, as the only charge it can have, and give the molecule a net 0 charge. So this would be copper 2 oxide. Similarly here, we have chromium is our metal, and we have chloride is the nonmetal. We know what charge chloride wants to have. It wants to be -1. And we have 3 of them. So we're going to have -3 from the chlorines, -1 from each. So if the whole thing is going to be 0, that means the chromium must be +3. So it would be chromium 3 chloride. All right. So with that in mind, why don't you try to solve these next 3 here. So we have silver and nitrogen, cobalt and iodine, iron and oxygen. So go ahead and pause the video and give those a try. All right. So I already have these set up with the names of the metals and the names of the nonmetals properly written. Really what we're trying to figure out here is what is the charge on those metals. We know that we have to put the charges in because these are all metals that have at least the possibility of a variable charge. And let me see, do I have that here? Go back real quick to the periodic table. There it is. Okay. So remember, these two columns here, we know exactly what the charges on those are going to be. Same thing with the aluminum here. We know what the charge on that is going to be. The ones that have possible variable charges are these metals here. Really, we should include polonium in that as well. So it's mostly the transition elements, but there are a few metals here that we do have to include as well. So any of these metals, if they are in an ionic compound, we have to specify the charge on that. But if the metal's in the first two columns, or if it's aluminum is the one exception on this row here, that is going to, those are only going to have one possible charge, so we don't have to specify the charge in those cases. But any of these transition elements, and then the few little elements down here, a few little metals down here, we have to specify the charge. So in this case, and again, we're using the nonmetals to determine what the charge on those metals are. So nitrogen would have a charge of -3, which means that we need +3 from the silvers to get an overall net neutral molecule. We have 3 silvers, so the charge is not going to be +3 on each of those silvers. If we had +3 from each silver, we would end up with a molecule that had a charge of +6, and that's not what we want. So instead, each of the silvers is +1. So this would be silver 1 nitride. The next one here, we have iodine. Each of those iodines is -1. So we would have -4 from all of them put together, which means that the cobalt has to be +4 to get our net neutral molecule. And then lastly here, oxygen -2, just like it was up here. It's not going to change just being in a different molecule. So we have -2 from each of the oxygens, which means we have -6 total, because we have 3 oxygens, which means that we need +6 from the irons. So if we need +6 from all of the irons put together, that means that each of the irons is going to be +3. And that is what we report. The number we put there is the charge on each of those metals, not the total charge of the metals. This, by the way, iron 3 oxide, has a common name. We normally just call it rust. Alright, we'll call it there for this video. In the next one, we will start looking at the last kind of ionic compound that we're going to see, which is polyatomic ions in ionic compounds. So we'll see you there.